Hey everybody, it's Ripley back again. Today we're going to talk about polar coordinates. Now you've already seen these, so this is going to be a super quick and easy review from pre-calculus. I also have more extensive videos in my pre-calculus videos if you'd like to check those out. So again, it's a review, so we're not going to go too much into theory. Just remember that a polar coordinate, instead of x, y, this would be a rectangular coordinate, right? You'll sometimes hear this referred to as Cartesian coordinates as well. We turn that into r comma theta. So if I've got some point out here in x, y land, then what I've got is theta is the angle made with the horizontal, and r, go away, really? You're going to show up while I'm trying to record my videos? And r is going to be this guy. So you can kind of see it's pretty easy to see where the fact that your x coordinate and your y coordinates can be really easily defined. We know that x is going to equal r cosine of theta, and y is going to equal r sine of theta, right? Those are the two biggies. Let x, well, not let x is r cos theta and y is r sine theta. A lot of students will be like, Ripley, why are we doing these things? Well, because it is a heck of a lot easier to describe some crazy curve like that. Remember the, like, what is it? Oh, let's see if I can do it. Like the four-petaled rose. Oh, I screwed that up. Oh, that's awful. Close enough. It's a lot easier to describe this guy using polars than it is to describe it using traditional rectangle. I can't even remember the formula for it. Was it like, I think it was r equals sine 2 theta? Something like that. Maybe we'll play with it. I've got the grapher out so we can figure out what that is in a little bit. Okay. The other thing to remember, excuse me, is that we know that x squared plus y squared is equal to r squared. So what we're doing is we're building bridges between rectangular and polar coordinates so that we can use those bridges to solve problems, right? So notice we've got polar, r and theta, and we've got rectangular over here. We've got polar, r and theta, and then we've got rectangular here. Last but not least, we know that the tangent of theta is equal to y over x. But we got to be really careful. Remember that when I solve for theta, I would take the inverse tan of y over x. However, the range of inverse tan is from negative pi halves to pi halves. It's going to spit out a value somewhere, somewhere between these two values. So you got to be careful. Remember, your calculator will give you a value here, but if you've got something, wow, I'm standing up, and I think sometimes when I work standing up, it's really hard for me to draw a Cartesian axis. Axes. All right, so let's be a little more deliberate. So if you got some point over here, let's call this negative 3 and 1, right? This is the point in rectangular, negative 3 and 1, and I want to convert that, and I want to use inverse tan to figure out theta. Well, I got to remember that. Let's see, inverse tan, if I'm building this thing like a right triangle, inverse tan of y, let's see, 1 over negative 3, right? Y over x is equal to, well, let me grab my handy dandy calculator here real quick. Second, inverse tan, inverse tan, negative 1/3 in paren. Let's see what mode. I'm going to change the mode really quickly to degrees so that we know exactly what degrees we're talking about here, which is fine. I just got to remember that it's like that so I can change it back. I hit enter and I go to, because apparently I made an error, inverse, did I put a minus there? I did, what a jerk. Negative, kapow. See, even I can be a moron. That says negative 18 degrees. Well, clearly, again, I'm moving quickly because you've already seen it. This point right here, remember, I draw my r out to it, I draw my theta around to it. This tells me negative 18 degrees, which tells me that angle right there, that theta is equal to negative 18 degrees. So how do I get from hither to thither? Well, this is just what? 180 minus 18 degrees, which is 162 degrees. All right, so you got to remember that. You got to be a little bit careful with these. Okay, all right, what else do I want to do? Let's talk about functions of these guys real quick. So in polar coordinates, we draw these functions like this. I kind of want to remember what how to draw that. I can't remember the equation for it. I think it's like sine 2 theta or cos 2 theta, something like that. I don't know. We'll try it. Like I said, we'll putz around with it. The r as a function of theta. So let's keep it simple. R equals sine of theta. Well, hopefully you remember from your pre-calc days that this is actually a circle of radius 1/2 that opens upwards on the xy plane or on the r theta plane, right? Which is easy to figure out. I know that when theta is 0, right? If I wanted to build a tree, a coordinate tree, my thetas would be here, my r's would be here. I'd stick theta, I'd stick pi halves, I'd stick pi, I might stick pi fourths, 3 pi fourths, pi 6, 5 pi 6, etc. All those things. When theta equals 0, r equals 0. When theta equals pi halves, so up here, right, I'm opening this up. I will say in the calculus of polar equations, or of polar coordinates, I'll say it opens up like a Japanese hand fan. So as theta opens up, we get all these points. So let's say at pi fourths, right? We know pi fourths lives right here. Sine of pi fourths is root 2 over 2. So it would be right there. Sine of pi halves is 1. So I'm there. Uh-oh, wait. 3 pi, or sine of pi is 0. Wait a second here. How about 3 pi fourths? Oh, root 2 over 2. So this whole thing is drawn out one time for theta between 0 and pi. So we got to be careful, because I don't know if you remember this, but the default setting on your graphers when you're doing these guys, let's do this one real quick, is it's typically 0 to 2 pi or negative pi to pi depending. So let's look at this guy. Let's look at our, let's look at our window. Yeah, 0 to 2 pi. So when I go to graph this thing, it's going to give me a little guy. Graph, let's see, y equals, did I not get it in there? Sine of theta. We're good here. Let's graph it. Well, that's interesting. Let's go back here. Ooh, let's troubleshoot this thing. Why is it doing it? Let's go zoom. Let's go zoom square and see what happens. Oh, something crazy is happening. Let's go. Oh, you know what's happening? This will make you giggle. You remember when I said, oh, it's no big deal if you change modes. It's because we're in degrees. It's only doing the first 6 degrees of the thing. What a moron. So bam, to radians, enter. I wonder how many of you caught that, you smart little monkeys. Bam! There's my circle. Hard to see. So let's tweak our window a little bit. Let's go zoom, see if we can get to zoom square. Well, bam, it's terrible, so I got to manually do it. X min, let's go negative 1 to 1. Right? And let's go y min, let's go 0 to 2, just because. Let's go 0 and 2, so we can see it. Graph. There it is. It doesn't look like a circle, it looks like an ellipse. So if you remember, you can go zoom square, which is 5. Hi. Oh, isn't that pretty? Okay? Easy peasy. Now, you didn't see it do it because it did it over the top of itself, but this actually carved out the circle twice. It went through twice. And you can always check, like one thing that I always do if I'm like, oh man, I do not know, I don't know the what the range is to get the whole curve. So I'll just tweak my window a little bit. Instead of going from 0 to 2 pi, I'll just go in and be like, oh, okay, let's do 0 to pi. And as you just learned, you got to remember what you did, because sometimes you're like, what just happened? And there you go. So you know that the whole thing gets carved out in pi. All right, now what did I say? Let's go zoom standard again. It's going to be small, I know. Zoom 6. It'll be tiny, but let's try and draw that. What did I say that was? At the cos of 2 theta. Let's go sine of 2 theta because it'll be easier. Let's go 2 theta m prim. Let's do my window. Excuse me. Let's go. Oh, I guess we could zoom in. Let's graph. Ooh, that kind of looks pretty good. Let's go zoom in. Remember, when you hit zoom in, it always sets it at the origin. Oh, yeah. I was right. That's pretty cool. Let's try zooming in one more time and see if we get the whole thing. Zoom in 2. And hit it again. Yeah, that's cute, but it's not quite as cute as we want it to be. Let's go zoom out. 3. Hit enter. Okay, that's better. Now, let's look at the window real quick. Did it work from 0 to pi? Was the whole thing carved out in 0 to pi? Well, nope, it took from 0 to 2 pi. Let's tweak it and go second pi, and then graph it. Yeah, see, only half of it gets carved out. So this curve, y equals sine 2 theta, excuse me, takes an entire 2 pi to get it done. So don't freak out. Just go back to window. Check your parameters as far as theta, x, and y. I guess that's not the greatest way to refer to that. Whoops. I want 2 pi, and hit enter, and then graph that sucker. There we go. It's beautiful. Okay, easy. You've done this before. There's no reason that this should make you nervous. Hopefully you remember that like r of theta is equal to cosine of theta. That's this guy. That's a circle of radius, or radius a half over here. Same sort of thing. Easy to prove. When cosine of 0 is 1, cosine of pi halves, which is weird because remember we're opening this thing up as theta opens up. Cosine of pi halves is 0. And then we know that, now remember this, ooh, this one's worth talking about. I like the way this one works. Let me change the color, bam. Okay, remember, so I know cosine of 0 is 1. I know cosine of pi halves is 0. So how does the bottom half of this curve get created? Well, because when I'm over here in the second quadrant, when I'm doing these guys, remember what cosine looks like. Cosine starts at 1, it goes to 0, and then it's all negative between 0 and pi, or between pi halves and pi. So from here to here, r is going to be less than 0, which does what? Well, hopefully you remember it flips it across the origin. So when I throw in r of 3 pi fourths, which would be right here, right? That's 3 pi fourths. I get cosine of 3 pi fourths, which is equal to negative root 2 halves. So I go up here, it's root 2 halves, but I flip it across the origin, and I get that point, which is kind of cool. Okay, and then hopefully you remember all those cardioids and all that good stuff, like this is 2 minus 3 sine theta, right? Remember what that thing looks like? You got the limaçon, like this thing will look something like that. Let's graph that thing real quick and then I'll be done, because I know you guys have already seen this stuff, but I did want to comment on it real quick. What did I say? I said 2 minus 3 sine theta. And we should probably, yeah, I think we'll be all right. Let's look. Yeah, there it is. Oh, it was upside down, which makes sense. It totally makes sense. Let's zoom back a little bit. Zoom out. 3. And hit enter. Yeah, there it is. You can see the little interior loop. Okay, I'm done. Oh, today's schedule is crazy. The bells went off a little early. Sorry about that. For those of you that don't go to school here, we have these things called bells. All right, have a wonderful day. And I will see you tomorrow. Hope you enjoyed polar coordinates. Talk to you later.